34.7. Okay, this video we're going to talk about how to determine enthalpy change of reaction using calorimetric method. But before that, okay, I just want to have a clarifications. For the standard enthalpy change of neutralization, we are talking about the combination of H plus and OH minus. During this bond formations, okay, we will release negative 57.3. So we are considering this kind of neutralization. But you have to pay attention. For these, we also having a neutralization. Okay, these are the base plus acid. But for these kind of reactions, okay, the enthalpy change will not be equals to negative 57. These will not be equals to negative 57.3. The reason behind is, okay, you can see that we will have solid for the base. So for this solid, first of all, okay, when we need it to react with the acid, first of all, they have to ionize, okay, to become iron first, okay? So they will have to break the ionic bond. And at the same time, okay, for some of the iron, for example, in this case, the calcium ion and also copper 2 plus ion, they are not react okay, in the neutralization. They act as a spectator ion. But at the same time, this spectator ion will also solvated by the water molecule. So it is just like Cu2 plus in the middle, and then you have the OH minus, the OH surrounding it. So this kind of attraction between the water molecule and also the metal ion, they will also release energy. So you'll find that again, not only we have to break the bond, but also you have bond formation. So all these things will be adding up. All these things will be adding up to the enthalpy change. So therefore, okay, the negative 57.3, we are just talking about, or we just simplify the whole things. We're just talking about H plus combined with an OH minus to give H2O. So if you have similar reactions, okay, like this one, a very typical one, where you have alkaline plus acid. Okay, you got alkaline plus acid. Remember the difference between alkaline and base, okay? The alkaline is a soluble base. It can dissolve in water, okay? So therefore in the process, okay, you will find that there will not be extra energy required to overcome the bonding between the alkaline compounds, okay? So for this kind of reaction, that will be 57.3, but for this, it will not be equals to negative 57.3. It can be more than that, or more negative than that, or it can be less negative than that, okay? It depends on many other factors, okay? So let's have a look of the example that we're going to talk about, okay? So this one, okay, we say that enthalpy change of reaction. Okay, so enthalpy change of reaction, we will give a graphical, or we'll give a graph right there, okay? So using graphical data, we're going to find out the maximum temperature increases, okay, in the process. So have a look of the reactions. Step 1, okay, what we are doing, we are having HCl, place it in a polystyrene cup. So you have something like this, you have a polystyrene cup, okay, and then you have HCl in it. Okay, and then the molarity is 0.5 and volume is 50 cm cube. Step 2, the temperature of the acid in the cup was measured with a thermometer at half-minute intervals. So I'm going to put a thermometer in it, and then every half minute I'm going to record the temperature change. So you'll find that all the data right here, will be a half-minute basis. Okay, so we have 1 minute 1, minute 1.5, okay, second minute 2.5, things like that. So what happened at third minutes? So you can have a look after 3 minutes. So we have 0.45 gram of magnesium oxide was added to the cup. Okay, so we will put magnesium oxide in it. Okay, we'll drop some magnesium oxide. You see that magnesium oxide and acid, actually they are neutralization. But just like what we have said just now, okay, this neutralization is not simply adding the H plus and OH minus combined to form water. So therefore the reaction is not necessarily equals to negative 57.3. So we can have a look what happened here. So after we add in it, okay, we expect there will be a temperature rise. Okay, so we'll express the temperature will go up, okay, and then the mixture was stirred thoroughly, so ensure that temperature evenly distributed in around, and temperature was measured and recorded. Okay, so it will be the or data that we taken afterward. But you check the time for taking the first record after adding the solution. It is already 3.5 minutes already, okay? And then the minute, like at the third minute, is missing. We don't have the data right there. But you should know that, okay, at this moment, we add the chemical. We add MgO right there. It should be the highest amount of reactants. So the reaction must be at the highest rate at this moment. However, we don't have the data here. So the highest temperature we expect will be happen here. If you pick this one, at this moment, this one should be around 32.9, right? Okay, so this one should be 32.9 degrees Celsius. If we pick this one, then we'll have a reductions, okay, on the highest temperature. So what should we do in order to find out this missing point? Okay, so basically you can see that, okay, after 3.5 minutes, the temperature of the mixture, it keep going down. The reason for this, okay, it is due to the heat loss to surroundings. Okay, so we can use this trend, okay, to estimate, okay, where will be the highest temperature is. Okay, so what we need, okay, is, okay, we have to draw an arrow. Okay, like the steps we showed down here, we draw an arrow. Where will we draw the arrow? We draw arrow telling us that when the chemical have been added. This is very important. So this part, okay, we're going to find out point right there. Second one, okay, we have to draw two lines. Okay, the first line, okay, I'm going to draw a straight line passing through here. Okay, so I will try to draw a straight line passing through most of the points, okay, that is going down, and then we can predict the trend, okay, of the temperature, or going up. So the second line that we're going to draw will be a vertical line. Okay, so there will be a vertical line passing through minutes 3, the third minute. So we're passing through here. So right now you can see that, okay, if we do like that way, there will be a intersection in between. So these intersections, the location will be slightly higher than the yellow one. Can you see that? If we look at it, okay, so these intersections should be telling you that, okay, it will be 33 degrees Celsius, which will be larger than the value just now we saw. Okay, this will be 33 degrees Celsius. So you may say that, oh, there is only a slight changes, okay? Slight changes, I agree. However, the exam, okay, require you to know these techniques. Okay, drawing two lines, okay, and then find the intersections. So this explorations techniques is very important. And if you just random pick this one, even if you just like 0.1 degrees Celsius difference, they will say that you don't know, this is not the highest point, so therefore they won't give mark for that. Okay, so this will be a very important skills for you to find out the highest temperature of the reactions. So we will draw two lines. Okay, one will be predicting the trend, okay, of the temperature force. The other one will be the line at which the moment that we add the chemicals, and we expect that the highest temperature should be happen at that point. Okay, so this one, the highest point will be 33 degrees Celsius. So what we're doing right now, okay, write a chemical equation for the reaction between MgO and also HCl. So we have MgO HCl, okay, we need 2H for the O, so therefore will be MgCl2 plus H2O. This one is just basically a chemical equation, so it is not a must for you to write the state for that, okay, but I just want to show you solid, aqueous, and also water. So that is part A. Part B, determine the maximum temperature change of the reaction mixture from the graph. Okay, pay attention. Right now we're looking for temperature change. Okay, so you have to see that, okay, we are talking about changes. So therefore you need a subtractions in between, okay? So the highest point, okay, it will be 33 degrees Celsius. The lowest point, we are talking about this one. So this one will be 26.8, I think. Okay, 26.8 Okay, so this one, okay, after subtractions, you'll find that it will be 6.2 degrees Celsius. Okay, so part C, okay, we're going to calculate enthalpy change of reaction. That means we're talking about this reaction. Okay, we're going to have we'll find out the enthalpy change, okay, for this. Okay, so because this is a reaction, so you're talking about MgO and HCl. So actually we are trying to find out the enthalpy change of reaction per mole of that, okay, instead of just basically enthalpy change in it. So for right here, okay, we have to find out the energy release first. But before that, okay, it seems that we don't have the mass of the solution. Okay, so I think we may need to find the mass of the solution first. So mass of water, or you say the solution. Okay, I think the solution would be more, it would be much more better. Okay, right here, mass of solutions. Okay, we assume that the specific capacity and density of the reaction mixture are the same as those of water. So we use this density to help us. Okay, so we have 1 times, okay, it will be 50 cm cubed, so it will be roughly 50 gram. So some of you may say that, if I add 0.45 gram magnesium oxide in it, then the total mass, should it be increased? Correct, okay, in general, it is, okay, but however, we can, in this moment, okay, we can just ignore it, okay. So it will be like 50 gram, okay, we just look at the solutions, okay, of HCl. Next, okay, we're going to find the energy release. Wait. So the energy release will be equal to mc delta T. So M will be 50, C will be 4.2, delta T, okay, will be 6.2 K. Actually, it is also equivalent to the K. Okay, so this one, the energy release will be 1,302 joule. Okay, and then next we're going to find out the number of mole. But right here, okay, we got 2 number of mole given to you. One will be HCl, one will be MgO. Okay, so we're going to find each of them individually. For HCl, we can use MV to help, so we'll have 0.5 times 0.05. So for the HCl, it will be 0.025. Okay, and then that will be 0.025 mole, and the other one will be MgO. So the MgO, you got like 0.45 over the mass of Mg, which is 24 plus 16. Okay, so for these calculations, okay, we can find it will be 0.0112 mole. So obviously you can see that these two, okay, they are not really a product of the others. Okay, it is not multiplying. 0.0112 will not equal to 0.025. So I think right there, okay, we have to concern about the limited and excess reagent. Okay, so to simplify the whole process, okay, we can just simply say that, okay, because 1 mole MgO reacts with 2 mole HCl. So at your in your mind, okay, just think about this one. If you need 2 mole, then that will be 0.0224 mole of HCl. However, okay, we just have 0.025, right? Okay, so therefore you'll find that HCl will be in excess. So we can conclude that MgO is limited. Okay, so that means this energy release, it is the energy release when all the MgO have been used up. So right here, when we talk about enthalpy change of reaction, if you remember reaction, we didn't have a specific target, okay, to talk which one have to be 1. But right here, MgO is the limited one, and also its unit is 1. Okay, so for us, okay, we're going to write down the enthalpy change of reaction per 1 mole of MgO. I write explicitly, okay, to tell them that whenever 1 mole of MgO react, okay, how much enthalpy change will be done, okay. So this one, okay, because it is an heat release, okay, temperature rise is an exothermic reactions, so I know that this will be negative 1302 over 0.0112, okay. So the answer for this one, okay, it will be negative 116,250 joule per mole, okay, joule per mole. Very close to the edge. So this one, okay, at the end, okay, we would like to consider that, okay, the whole reactions, okay, enthalpy change of reactions for this will be negative 116.25 kilojoule per mole, okay. So the statement, okay, we will write therefore the enthalpy change of reaction is negative 116.25 kilojoule per mole. Okay, so remember, you have to check every time after you finish doing the math, okay, you have to check whether the sign have been there, whether the unit is correct, okay. So this one, even though it is a neutralization, but as I have said before, okay, you need to overcome the attraction between the MgO and then the Mg, when it's solvated in the water, they put in the water, they will also have some energy changes, energy release in the process. So all these things, okay, will be taken into account, okay. So the result, okay, it will not be equals to negative 57.3 like the reaction between H plus and OH minus, okay. So this sections, okay, I want you to pay attention to the skills of drawing this. You can see the textbook, okay, the answers, okay, will be like that, okay, draw a line, okay, passing through the remaining dots, okay, and then we expect, okay, the highest point will happen at the time that where you add the chemical. Remember, when you add the chemical here, I will suggest you to draw an arrow, so therefore you won't shift to here, you won't shift the line here, or things like that, okay. So these 2 points are incorrect, okay. So just want to include a public exam to let you see, okay. So you can see that, okay, this one, okay, we also have some data here, okay, we got points, okay, on this side, and then we say that at this moment we add chemical, so we will expect to draw a vertical line at this point, a vertical line at this point. Wait for a while. Okay, we will draw a vertical line at this point, and then, okay, on the other side, okay, you will find that we will have some dots to indicate the temperature going up here, going up. So therefore, I'm going to draw another line right there. Okay, so we'll have another line. So what you need to do, okay, basically, what you're going to do, okay, just basically find out the interactions, okay, for this. So you find out the interaction. Wait for a while. The interactions, okay, will be right there, okay. So this is the techniques that you need to know. So the last one, okay, is about determinant or determination of enthalpy change of formation. We have talked about neutralization. We have talked about neutralization. We use a cup, remember that, okay, and then we have a thermometer there, okay, and then combustions, okay, we put water, okay, above, and then we have a thermometer there, and then we just burn the things down below, okay. So we have two calorimetric method to find out the enthalpy change, okay. However, for formation, okay, we do not use this method, okay. There are some limitations for formations, okay. Well, let's have a look. The first one, okay, you have to find out some of the formation is highly exothermic. It's not safe to carry out. For example, you can find out, okay, some of them is like negative 1,207 something, negative 2,000 something. Or some of them, okay, would be like maybe this one, okay, we were having like formation of water, okay, right, wrong. Formation of water, it should be half O2. So formation of water, but on the other way, okay, you see that this one is formation of water, but at the same time, actually, it is also a combustion of hydrogen. Is that right? Okay, both of them, they share the same equation. Combustion of hydrogen, you burn hydrogen. Do you have a container that you can hold the hydrogen in it when they have explosion, and everything will be fine, including your thermometer? So you'll find that some of the reaction is highly exothermic, we cannot safely carry out. Second one, the constituent elements are in different physical state and they cannot be mixed well. Let's have a look at formation of this one, okay? What we have should be NaH2, and then we have C, and then we have O2, okay, for the formation of NaHCl3. Have a look of the state of them. Some of them are solid, some of them are gas, and solid. How can you mix, okay, in a container? You mix the gas and the solid evenly distributed, okay, and then they were homogeneous in the container. The solid must fall at the bottom, is that right? So how can these happen, okay, to allow them to mix well, to have the reaction to go on? Third, okay, third reasons, okay, we'll have the side reaction, okay, that may lead to formation of other side product, and they may also affect the enthalpy release. For example, if I want to talk about formation of carbon dioxide, okay, we have the equation like C plus O2 to give CO2. Is that right? However, when you have C plus O2, you may give CO. So this process, you may have like releasing energy, but that is the formation of carbon monoxide. When these two things mix together, then actually when we measure the enthalpy or the energy release, it is not really that precise to say that 100% it is due to the formation of carbon dioxide. Due to these reasons, okay, it is difficult for us to find out experimentally or the enthalpy change of formation. And what we do next, okay, that will be next chapter, will employ a calculation called Heck's law to help us to think about how to find these enthalpy change of formation. Okay, so to summarize, okay, these videos, first of all, you learn a new techniques. Okay, these techniques, okay, is very important. You have to draw arrow at which the chemical add, and then you have two lines here. One will be talking about the trend like going down of the temperature. The other line, okay, it will be the moment that we add the chemicals. The intersections, okay, it will then be the highest temperature. Okay, make sure about that. Okay, and then can we use standard? Can we measure the standard enthalpy change? Okay, experimentally. Okay, just how we said that. No. Okay, because some of them is highly exothermic, and constituent elements are in different physical state, cannot mix well, and some of them you may have side reactions, so that we cannot really know that the energy release is only due to that reaction. Okay, so that's all for this video, and also it is the end of this chapter. Okay, so do spend time, okay, to write notes and also finish the chapter exercise. Okay, bye-bye.